Yeah.
Shall we start? Okay, so welcome to the Alice session. I will give an overview of recent results, and I will say what Alice is planning for the near and further future. And I will also, of course, emphasize a little bit the collaboration that we had with Ukraine, especially Kharkov and the Kiev institutes. Now, to start with a little bit of history, just one slide. In fact, it was commemorated yesterday that an Alice delegation visited Kharkov already in 25 years ago. And immediately, already 2 years later, there was a Ukrainian technology mentioned in the technical proposal for the Alice detector. In the upper left of this slide, you see an overview of the entire Alice detector. It's basically a detector that measures particle production at mid-rapidity, so it's not full coverage. It measures in basically 2 units of rapidity with a big tracking system and calorimetry outside, time of flight, all those things. Then on the right-hand side of that same plot, you see a big device that is a muon spectrometer. It has, of course, an absorber to throw out everything else but muons. And this detector measures synchronously with the central part. Now, the specific thing about heavy ion physics, what Alice does, is that we want to measure events with a lot of particles. The Alice detector was designed to work with 16,000 particles in these 2 units of rapidity. In reality, when the measurement started, the density went down a bit. So the detector is actually working perfectly for its purpose. Now, another issue in Alice is that we want to measure low momentum particles. And this is where the Ukrainian technology came in. Because especially in the center of this detector, the inner tracking system, that is fully based on silicon detectors, but it's complemented with aluminum on Kapton cable technology that allows us to keep the material budget in this detector very low. And that is why we can measure pions down to 100 MeV momentum. At the same time, because some of the detectors in the inner tracker can also measure the energy loss, we also have particle identification in that low momentum region. Now, the inner tracker is big for a silicon device. It's 5 square meters of silicon, which, let's say, 20 years ago was quite a challenge. It's complemented by a large gas volume. It's the blue part here. That is a time projection chamber. And this time projection chamber is actually what limits our data taking at this moment. But the good thing about time projection chamber is that it can measure many, many tracks with measuring the energy loss and therefore do particle identification. So this is the heart of Alice. And I think I can say that the performance that we are having today would not be possible without this Ukrainian contribution. I would also like to say that we had a very open collaboration building this detector. We had really a joint system design where all the involved laboratories were suggesting improvements in the system. And for example, the layout of the front-end chip in the silicon strip detector was adapted to match the cable technology that was going to make the connections. On the other side, the cable technology was improved, optimized for smaller pitch connections than were done before. We also had Ukrainian people coming to European labs and even to companies to show how to use the technology, because it's not standard wire bonding. This saves a lot of material. But of course, if it's not standard wire bonding, then it's a bit more difficult to assemble things. And this, we got lessons from Ukraine on how to do those things. Okay, now going to the ALICE physics. ALICE is mainly designed to look at heavy ion collisions, and the idea behind that is that an ion is a relatively big object. We use lead in ALICE that has more than 200 nucleons. And if you collide the two nuclei, then we produce in the collision a large system of quarks and gluons, in the early hot stage actually dominated by gluons. And what we want to do is to measure the properties of this. This is because these properties can also be calculated, at least to some degree, for example, with lattice QCD and other methods. And this means that we want to measure the bulk properties of this quark-gluon plasma. We want to measure the density, and that is where the jet medium interactions come in. If you have a high momentum parton that traverses the medium, then it interacts with it, and this is measurable. We can use electromagnetic probes, and this is interesting because, for example, photons do hardly interact with the medium, of course, not even with gluons. And there are also different kinds of quarks, the light quarks and the heavy quarks, and they also interact differently. Of course, it's impossible for me to summarize everything, but I will give a few highlights of recent results. Now, a wealth of data is available, and actually in this week there is a big conference in our field called Quark Matter, where we have 36 talks, 120 posters, and at the same time we had 60 papers in preparation. I think actually some of the 60 are already finished by today. This is rapidly evolving, and therefore it's impossible to summarize all of this in just half an hour. And I will make a personal selection of a few highlights that hopefully give you the idea, the understanding that this field is still is very active and rapidly developing. Just a summary of the table. What you see, we need to vary a lot of parameters to actually look at the quark-gluon plasma. So what we do is we measure with lead. That is the most challenging measurement because it produces the highest number of particles. Is to just use smaller nuclei, then you get a smaller system. And the other, of course, is to look at non-central collisions. So when the lead nuclei do not fully overlap, you also have a smaller system. Then, of course, in principle, proton-proton should be the baseline. To first approximation, a nucleus is a collection of protons and neutrons. I will show a little bit also results that indicate that this is not the case, but on the other hand, it's also quite similar. And then, of course, the intermediate case is proton on a nucleus. And from all this information, we have to derive the properties of the quark-gluon plasma. Just as an illustration, in the upper right, you see a typical central event in lead-lead collisions. So people working with proton-proton collisions can appreciate that measuring 3,000 tracks is something different than measuring 10 tracks. Okay, now the first and the simplest thing is just looking at particle production. If you collide nuclei, then you produce a lot of particles. And we always look at those as a function of either number of participating nucleons, as is done in this plot, or in related parameters. And what you see here is that the number of participants you can actually calculate relatively easy. The nucleus is a big object. You know how many nucleons are in a nucleus. So by ordering them in number of produced particles, you also can estimate what the overlap was. And from that, you can estimate the number of nucleons participating in the collision. Now, this number of participating nucleons, of course, define the total energy available and therefore should, to first approximation, give you the number of particles produced. What you can see here is actually a recent result that is also being presented at Quark Matter now. And that is that the evolution of particle production as function of the system size is not exactly is not corresponding exactly in xenon-xenon and in lead-lead. This is not fully understood. There are deviations from a straight line. The line doesn't go to zero and so on. That is understood because at these energies, actually, the degrees of freedoms are the quarks, the valence quarks in the protons, and not the nucleons themselves. But even then, there are deviations that are not explained by this, and they are at this moment not fully reproduced by models. So this is input for theory to understand better how particles are produced. Now, another interesting result from the actually, it has been developing in the past few years, but it's becoming more and more evident. There is a method that if two nuclei do not fully overlap, this is sketched in the top right, then actually the overlap region is not spherical. So you get an almond-shaped system. And of course, because we have a hydrodynamic expansion of this hot system, you get asymmetries in the angular distributions of particles. Now, I will not go into how the measurement is done exactly, but it's usually characterized by measuring Fourier coefficients of this distribution. And if you look at those, then you see here is the number of charged particles measured in the system, in the collision. And that is, of course, a measure also for the centrality. The larger the system, the more participants, the more particles you produce. So central collisions are on this side. And completely central, which of course has a very low cross-section that they just hit head-on exactly. There you don't expect this kind of asymmetry. And on the other side, where you have the peripheral collisions, you have actually a shape, a very sharp shape that is far from cylindrical, from spherical. And therefore you expect some asymmetries. Now, the surprise that we are seeing in recent years is actually that we see this in lead-lead, we see this in xenon-xenon. Those things are more or less understood, and actually they work quite well in models. But we see also non-zero asymmetries in collisions like this, proton-lead and proton-proton. And at least 10 years ago, this was not part of any model. Because in proton-proton, you have such a small system that you don't expect a material to be formed. You don't have statistical thermal equilibrium, things like this. So it should be going to zero, but it doesn't. And this is one of the puzzles that we have in this field at this moment. There are, of course, ideas. It seems to indicate that at these energies, there is so much energy available that you still have some rescattering after the initial quark and gluon scatterings, that you still have an approximation of a material where you can measure properties. This is just being presented and discussed at this moment in the field. And then a further thing I want to highlight is the chemistry. Again, maybe it's best to start with the lowest plot. I doubt if you can read it in the back of the room. But what you see here is for different particles, you see how many are produced relative to other particles. So these ratios in production, that's experimentally an advantage to measure ratios because quite some systematic errors cancel. If you do that, then you can measure the ratios, and well, you can see this is a log scale. There are 7 orders of magnitude in the ratios, and all of these ratios actually match, except maybe this one, with the lines, and the lines are the predictions from just a relatively simple thermal model. So this indicates that in the final hadronic phase, there is an equilibration between the different kinds of particles. And this is a very important ingredient because until now I've spoken about the quark-gluon plasma, but in fact, of course, we see the end of a chain of events. That is the production, the creation of the quark-gluon plasma. Then it's cooling down and expanding, and after that there is a hadronic phase where particles are produced, and they also rescatter. And this is one of the evidences of this. The thermal model is very old. And in fact, it was not expected that it would survive so long, but it's still alive and matching the data. Then on the top, you see another plot. It's also, this is again in units of number of produced particles. So that is, again, central events on the right, peripheral events on the left. Peripheral collisions are small, so you expect as I said before, you don't expect a full equilibrium system. But what you see here is that there is no sharp transition. When I started in this field 30 years ago, it was expected that proton-proton is just QCD, PQCD, it's understandable. You use this as a baseline and you subtract it from what you measure in lead-lead or gold-gold collisions. And then in a bigger system, you create this quark-gluon plasma with entirely different chemistry. This turns out to be not true. There is a smooth transition. There is not a step. So there is not a point where we suddenly create a new phase. And this indicates that the production saturates. So in fact, the models work there. This is the quark-gluon plasma as we expected. But in smaller systems, actually, there is a smooth transition, and this still needs to be understood how this works. Then I mentioned jet quenching already. Now, one thing that we can really calculate very well is high momentum transfer collisions. So you have 2 partons from the 2 incoming nucleons. They collide and they produce another high momentum parton, a quark or a gluon. Now, if at the same time all the other quarks and gluons at smaller x, that's lower momentum, produce soft degrees of freedom, so quarks and gluons and a quark-gluon plasma, then this high momentum parton has to escape from the system, and it interacts with this. The very basic measurement you can do there is to see how it loses energy by going through the medium. And this is what we do with these plots. These plots actually indicate the ratio of number of particles that you see at a specific transverse momentum. And you can see that this is not constant. So that already indicates that lead-lead is not just a superposition of proton-proton, where you just have the same momentum spectrum and all partons fly away as they did before, but just more of them. So this has a somewhat more complicated structure. Now, the latest piece of information that we have, I mean, these structures are more or less what we expect. But the latest information we have is that we see exactly in xenon-xenon, we see quite similar structures, and actually also quite similar in magnitude. And this is not fully understood yet. Probably an interplay between the path length. A smaller system means that the quark traverses less material before it escapes, and the density of this system. So models are being tuned, and we will see what survives there. Then there are many more things we can measure, but now I want to go to a little bit more to the future. You see here a plot that is just the invariant mass of proton K0, and this mass, of course, you can see the lambda c following this decay. We have a very good tracking system, so in principle we can reconstruct those, but the cross-section, at least for us, is not very high. I probably didn't yet mention it, but the Alice detector with the time projection chamber is not as fast as CMS and Atlas, so we don't have the same number of events. And in addition, because this is a decay with a not very long decay path, you automatically get a large combinatorial background. So this is with the statistics that we have now. You can see the peak, but you can understand that measuring anything using this is quite a challenge. We need this because this contains, of course, a charm quark, and that has mass, where the U and the D and even the S at these NGs and in this medium can be considered to be approximately zero mass. So we need this information, and that means there are two ways to attack it, and of course we want both. We need more data, and we need a better background rejection. So that's the goal of the Alice upgrade. We want to measure heavy flavon mesons and baryons down to low momentum, because in the end we're looking at thermally equilibrized systems with relatively low momentum particle production. We want to look at charmonium states. I had no time to explain that, but you can imagine that a heavy system that is embedded in a hot medium will melt, and that is what is called dissociation here. And also, if there are many quarks, they can recombine and form resonances again. So these are interesting things to measure. So what we need in the end is minimum bias events. That means we have all kinds of impact parameters, and therefore we scan the full range of system sizes and system shapes. But at the same time, if you do that, dedicated trigger is, of course, not possible. So these are limitations on how we can do the upgrade. Now, the upgrade for at least the coming shutdown, so actually we are going to install these things next year, is a full replacement of the inner tracking system. I will say a few words about that, but we use the MAPS technology for the electronics. We also reduce material again so that we improve the resolution on where the tracks point. So if you have a decay that happens not in the main event vertex, then we can distinguish it. We do that very easily now, of course, with weak decays like the K0 and the lambda. But as I showed for the lambda C, this is still a challenge to get a good signal to background ratio. We use the same technology to improve the muon tracker. Again, time doesn't permit to explain all the physics that we can do by measuring muons in the forward region. But this also needs an upgrade, and we will do that by placing an additional vertex tracker based on the same technology in front of the muon detector. So again, this part is the muon tracker. There is a big absorber here, and then just in front of that will be, again, a vertex detector. Then there will be trigger detector replacements. I cannot go into that. And online and offline, there is a total rewrite of the software for online, and that also affects what we do in the offline software. And we optimize the system to be able to push through more data through the same channels. So this resulted in a lot of reports. Of course, you see the main ones that I discussed here. It's the inner tracking system with the time projection chamber around it. I will say a few words about the TPC also, and then the muon forward tracker. And then there are many other parts that have to be adapted also. So first, the inner tracker. There will be a new inner tracker, and we will reduce the pixel size. At this moment, it's more like a few hundred microns size in Z direction and 50 in the R phi direction. By reducing the pixel size, of course, we have a better constraint on where the track points. At the same point, you see the last point here, we reduce the size of the beam pipe, so we get closer to the interaction point and therefore closer also to the decays that have a short decay path. Because we use this MAPS technology, we have low noise, it's fast, it can have a low material budget. And this is all because in this technology, you integrate the electronics with the sensor in one silicon wafer. So you get rid of making connections between them. You get rid of all the mechanics to hold those things together, to hold the electronics and the sensor together. Also, the groups working on this chip did a very good job to reduce the total power consumption, and this also reduces the cooling system, which again is reducing the material budget a lot. Of course, this resulted in a very big system. We have extended a little bit the ETA coverage, the rapidity coverage, and that means we now have 10 square meters of silicon, where in the old system it was a bit more than 6, I think, in total. And we have basically a 12 gigapixel camera. Okay, I will skip this, but there are many people are interested in using actually this chip design. Now, key technology here is this monolithic active pixel sensor. So it integrates readout with the sensitive element. This is an indication of how it works. In the top layer of silicon, you have the electronics. You have actually quite small region of silicon where you generate charge, and this charge, it diffuses to a diode where you measure it. This is relatively fast because the distances are short here. And so what we do is we take this wafer, which comes from the factory at 700 micron thickness or so, and we cut it down to 50 microns. So this is really, and this includes already the electronics. So it's a very thin detector. And again, this is where the Ukrainian technology also comes in, because we use, again, aluminum on capstone cables. Aluminum is much better in terms of material budget for the conductivity in electricity. And this actually connects the whole system. I see I have to speed up a little bit. These are just pictures of how things work. For example, this is the power bus I was talking about. And you can see here that things are actually in progress. They are working. Now, I really want to say also something about the TPC. The TPC, this is a picture of what the TPC has to do. You get, in the drift volume, you get all the events just randomly as they are produced. And what we had what we have actually in the current system is a gating grid that actually switches on the TPC, makes a drift volume, you collect the charge, and you measure the arrival times. That's how a TPC works. But if you want to go a lot faster, then the traditional TPC has a lot of backflow of positive ions in the gas, and this starts to distort the electric field and therefore the shape of the tracks that you measure. If you want to avoid that, then you have to prevent this ion backflow. And if you do that, then you can get rid of the gating grid and you don't have to switch on the drift voltage all the time. So this can speed up things. And at the same time, if you are a bit smarter in analyzing the incoming tracks, you measure all of them continuously, then you can actually work without the gating grid. So this should allow the TPC after the upgrade to work with the 50 kilohertz interaction rate of, instead of what we do now, around 1000 Hertz interaction rate. Okay, I will skip the technology that allows to reduce the ion backflow, but it's based on GEMS, but with a few improvements for this harsh environment. Then the muon detector is again, it has a big synergy with the inner tracker. It uses the same MAPS technology, and this means that you can also see it as a sort of extension of the inner tracker, but just with a forward region. Okay, a few words about the improvements. These are plots that actually show the improvement. You can see with the current ITS and the upgraded ITS in all the plots. And you see there are huge improvements. For example, this is the pointing resolution, which is one of the parameters you use to select tracks from a decay. And there are factors of improvement in those. The TPC, of course, a main concern here is, as I said, that you build up charge in the drift volume, and therefore you start to distort tracks. That has been studied in detail, and there is a region. This is actually a very conservative region. Measurements in the lab and predictions actually indicate that we can work somewhere here. And this is ion backflow percentage, and this is then the resolution on the momenta. This, of course, results also in physics improvements, and there are a few plots here. In view of the time, I can only highlight, for example, the D0, where you get a factor of almost 2 in aerobars, and you get larger improvements in the lambda C. In fact, what we get is we get 10 times more events, and we get another factor 10 in resolution for these decays. So this gives a factor 100 in the measurement, and therefore, again, square root 100, factor 10 in the aerobars. Okay, what comes next? I'm sorry, I will overrun 2 minutes, but what comes next, and this is an idea. It's not an official upgrade yet, but I want to mention it because it's an active community looking at new things to do in Alice. And one of the new things is that the parton distributions at small x even in protons, but especially in nuclei, are not so well known. And now that we enter the era of precision measurements, you want to know actually what is coming in. If you want to calculate a scattering of partons from the nuclei, then you would like to know what their initial momentum distributions are. There is an opportunity in Alice to measure forward direct photons. That would give you a clean probe of small x gluons. And that gives complementary information to open charm production. The advantages, of course, of direct photons is that there is no final state interaction, so you have a better sensitivity on these distributions. Of course, this is also tricky because photons are not only direct photons, but there are many particles that decay into photons. And a very large source of background is actually pi-0 decay, and pi-zeros are abundant. So this is the challenge for this kind of detector. Alice has looked at places where it can be put. There have been Monte Carlo studies in how well it will perform. And there are also hardware efforts to actually start building prototypes of this detector. These are plots showing how you can separate 2 photons coming from a very high momentum pion, and you can still separate them. That means you can measure the pi-0 and you can subtract it from what you measure so that you get the direct photons. Now here there is again a very significant contribution from Ukraine, from the LTU, in fact, and that is using you want a small Molière radius in a photon calorimeter. And you can do that best by having heavy material as absorber, then measurement layers with as little as possible air and empty space. And this gives you, this you can again do with using the Ukraine technology, because you can compress the geometrical size of modules. As I said, the prototypes have been made for this, and these are a few photos. There have been beam tests, and this is progressing very well. At the moment, this project is being discussed also in the ALICE management and in the physics committee, so that we can evaluate how well this is going to work and if this should become a big project. So, summarizing, we know things about the quark gluon plasma. We know that it is a very low viscosity medium that is very strongly interacting. The density is higher than we thought. And we also, the viscosity is much lower than we thought 30 years ago. So a lot of progress has been made. Many things, if you adjust for this new knowledge, then many things can be explained, but we need more detailed studies. And for that, we want to do upgrades, and there the Ukrainian contribution is essential. This is showing a detector that is installed now. This is the new detectors being built with the Ukrainian technology, and that is the future ideas for the focal. Also, Ukraine has contributions in data analysis. I will not go into detail. There is connection to theory, and for that will be additional talks. Just as a final note, I think we have a 25-year collaboration with Ukraine, and this has been extremely effective. These things do not only build a detector, you also build a community. You see myself here trying to blend in with the Ukrainian environment. But we had also many workshops and collaborations and exchange of people. So I think this is also very, very valuable. Thank you.
Thank you very much, Paul, for excellent presentation. The talk is open for discussion. Please, questions, comments. Yes, please.
I'm a very good question about the jet quenching.
Yes.
Is it correct? I understood correctly that this is quenching. You consider it due to interference of the different part of the jets, or?
Well, there are two components in jet quenching, and the calculations are often not combined, so that from the theory side there is some work to do. One is collisional energy loss, and the other is radiative energy loss, and the latter is interference of the radiation wave.
Okay, you have considered this. Okay, yeah. Thank you.
More questions? Yes, please.
Small comment. As for particle number ratios,
yes.
Okay. You see, the thermal model is really a very old model and used very good. But what I claim, maybe I will time to show, that in dynamical, we have a continuous result, continuous chemical result. And description, especially for pi-to proton ratio, even better, much better than in thermal model. So it's a good approximation, but for LHC system, it's not too accurate.
I agree with you, but two comments. One is that it's surprisingly precise after all these years for such a very simple model.
I will show more.
And yes, and the other comment I want to make is that we do see deviations, and for example, in the protons, but okay, I cannot open up this subject in an overview talk. Okay. But it's really surprising. After 30 years, it's still over 7 orders of magnitude. It's nice.
More questions? No questions. Let's just it again. Thank you very much. Now let us proceed to the next talk, which will be presented by Kirill Bugayev. Relativistic equation of states of hadronic matter and possible signals of 2QCD phase transition in heavy ion collisions.
Hello, everyone. My name is Kirill Bugayev. I'm thankful to the organizer for giving me a chance to talk about the realistic equation of state. These results are made by collaboration between Boglebov Institute in Kiev, between GINER, and between University of Oslo. Okay, as Paul already mentioned, there are many issues related to quark-gluon plasma searches. In fact, on my taste, the situation is paradoxal one. So already two collaborations claim they discovered a new state of matter. And we are sure that at high energies of collisions, we indeed see quark-gluon plasma. However, high theory is unable to answer these three main questions. Whether the confinement and chiral symmetry restorations are the same phenomenon or a different phenomenon at high baronic densities, whether they are phase transitions or crossovers at high baronic densities, and finally, what are the collision energy thresholds for this phenomena? To answer these questions, since high theory, lattice QCD cannot tell us true answers, so we need some new tool to analyze the data. And during last 2 years, the situation is slowly getting improved, because during these years, we developed new tool. This is multi-component hadron resonance gas model, and which allowed us to describe the data with very high precision. And using this description, we were able to find new irregularities in chemical freeze-out and to formulate some new signals of two phase transitions, which are expected in QCD. Due to lack of time, I cannot go into details, so I just will show more striking, on my taste, results. Okay, pardon. So what is hadron resonance gas model? In fact, this is van der Waals-like equation of state with hardcore repulsion, written for all hadrons and hadron resonances which are known from particle data group. Then, since it is equation of state, then taking the temperature, baryonic chemical potential, strange chemical potential, and the short isospin projection chemical potential, you can calculate all thermodynamic quantities. In particular, you can calculate charge densities. Then, knowing decay patterns, you can feed the data and get information about the so-called chemical freeze-out stage parameters. Chemical freeze-out, this is, of course, approximated picture, but it is assumed that this is a moment after which the hadronic composition of the system doesn't change, because at low densities, the inelastic reactions do not exist, and there are only elastic reactions and decays. Recently, we invented new equation of state, which is called induced surface tension. So it is system of two equations. One is for pressure P and another for sigma, which is induced surface tension. And it gives two advantages compared to other formulations, because we need only to solve two equations independent on the number of the different hardcore radii. So you can use infinite number, still you will need to solve only two equations. This is non-trivial task, because in the right-hand side, you have hundreds of integrals, two-dimensional integrals, which you have to calculate. Another advantage is that this equation of state allows one to go far beyond the van der Waals approximation. This is highly non-trivial fact, because this is virial expansion for one component system. That means with single hardcore radius. So this is second virial coefficient, this is the third one, and the fourth. And so the non-trivial part is that alpha equal to 1.25 provides simultaneously the correct description of the third and fourth virial coefficient of the gas of hard sphere. And therefore, our equation of state is valid up to very high densities. This is seen from comparing the compressibility factor. This is our equation of state. This is a solid curve. The dashed one is Carnagan-Starling equation of state, which describes 7 virial coefficients. And the dotted one is the van der Waals equation of state. And so you can see that up to this Pagan fraction, 0.22, our equation just matches the Carnagan-Starling. The same is seen for two-component or multi-component system. When you calculate the speed of sound, you can see that speed of sound of our equation of state, this is solid line and Carnagan-Starling, they differ by 1.5% up to 5 normal nuclear densities. So they just match. And remember that speed of sound, this is ratio of derivatives, okay? So using this equation of state, we were able to describe all data which exist from AGS to Alice energies. And I show just some results for most problematic ratios. This is so-called K plus to pi plus ratio. Just look into the black squares, and lambda to pi minus. You see chi-square are essentially smaller than 1. The best results obtained by our competitor, it is Peter Braun-Munzinger group, are much worse. For chi plus to pi plus ratio, the chi-square still is acceptable. It is 1.5 per point, while for lambda to pi minus, it is really very bad. It is about 7. But this is not only results. I show some results for Alice data measured at 2.76 TeV. Paul showed probably the Flores results. These results are published. So since our radii are fixed from the fitting of low energy data, so in fact we have a single fitting parameter. This is chemical freeze-out temperature. And you can see these are ratios, and this is deviation of theory from experiment in units of experimental error. And you can see that we have very good description with total chi-square per degree of freedom, 0.8. Okay? But yeah, one more thing that I have to say, that we included light nuclei and anti-nuclei. And there are problems with light nuclei description in thermal model. No one understands why light nuclei and anti-nuclei are so well described by thermal model. In particular, we can describe it, and I showed it on previous slide, with the hardcore radius for nuclei, which is equal to the hardcore radius of baryon. But you see, this should not be true, because, for example, hyper-antitriton, it has about 0.3 MeV binding energy only, and in fact, it's a very large system. Radius is about 1 Fermi. So how it can be described by a thermal model, we don't understand. Moreover, there is a problem with the conventional coalescence model, which cannot also explain the appearance of light anti-nuclei. Sometimes it misses by 2 orders of magnitude. And for this meeting, we described the very fresh data. So we got new data from helium and anti-helium. And in contrast to other groups, we use this induced surface tension equation of state and very simple formula known from nuclear physics, that hardcore radius of the nuclei consisting of A nucleons should be proportional to the third root from the number of nucleons. And again, we have single fitting parameter, and our chi-square became worse, but it is still better than what Paul showed in his talk. So it is just obtained, it was obtained yesterday. The conclusion for first part of my talk is the following. Now we are confident that around the chemical freeze-out region, we know hadronic matter equation of state with high precision. The second thing is that this equation of state, which we developed during last years, is consistent with latest QCD. An example is shown here just for zero baronic chemical potential. And then using this equation of state, we already can study irregularities at chemical freeze-out with high confidence. And this is my second part of talk. Again, I cannot talk and tell you in all details, but this is most striking result for trace anomaly as a function of chemical freeze-out temperature. Yeah, and you see that there are two peaks. One is 4.9 GeV square root of S, and another is 9.2 GeV square root of S. So this is AGS point, and this is RIG point. Why these peaks are interesting? If you look into the right-hand side picture, these are results of latest QCD groups. And this maximum or this peak, latest people used to separate hadronic world from quark-gluon plasma world. And so when we saw this, of course, we were puzzled and we asked the question, is there any relation between peak at chemical freeze-out and the peak in the phase boundary? In order to answer these questions, we used the model, which is well known. This is Shock-Adiabate model, which allows one to calculate the initial state in collision. 30 years ago, when I was a PhD student, I extended this relativistic model to the case with refers to the phase transition with arbitrary thermodynamic properties. And those days, we predicted some new signals, and 3 years ago, my PhD students found those signals in the data. But most striking thing in my mind is the following. And in order to describe high-density phase, we used the pressure of bag-like model with 3 fitting parameters, A0, A2, and A4. Because the force parameter was fixed in order to have the pseudo-critical temperature 150 MeV at zero baronic chemical potential. And so if you take literally those coefficients, which we obtained from fitting the data on the entropy per baryon, so we were able to find the number of degrees of freedom, bosons and fermions in all together. So it is a very large number, 1,770 degrees of freedom. The A2 coefficient can be used to estimate the number of fermionic degrees of freedom. It is 142. So it is really a very large number compared to elementary number of degrees of freedom in QCD. And my interpretation is that between 4.9 and 9.2 GeV, there may exist hadronic phase with partly restored chiral symmetry, because this number is close to the number of non-strange hadrons known from particle data group. It's funny that other group, in particular group from Gießen, headed by Wolfgang Kassen, also have a similar results, but we found it independently. So this is K plus to pi plus ratio, which they describe. They tried to describe it without chiral symmetry restoration in hadronic phase, and they failed. But then when they invoke chiral symmetry, partial chiral symmetry restoration in hadronic matter, so they can describe both of these data. Actually, I showed you the same. And moreover, their prediction for the crossovers are very similar to our ones. So you can see that the energy is about 4 GeV for chiral symmetry restoration crossover and about 10 GeV for deconfinement transition. Because they have transport model and they use finite system, so they do not see phase transition in contrast to us. They can see only crossovers. But it is really striking. And then I come to conclusions. So the first result is that hadron resonance gas model with multi-component repulsion allowed us to find out the signals of the first order phase transition to massless hadronic phase at the center of mass energies about 4-5 GeV, which were predicted actually in my PhD thesis in 1989. The second set of irregularities at higher energies, 8.8, 9.2 GeV, may be a signal of deconfinement phase transition from massless hadronic phase to quark-gluon plasma. These findings, together with the other group findings, evidence for existence of 3 critical endpoints in QCD rather than the critical one. And we hope that next year, Rick Energy Scan, and in a few years, NICA and FAIR experiment will confirm this result. Thank you very much for your attention.
Thank you very much, Kirill. The talk is open for discussion. Please, questions, comments. Yes, please.
Thank you for a very nice talk. I have a question related to your model. So you, as far as I understand, you included all baryon resonances from particle data group. How did you take into account the K widths of all resonances?
Well, they are also known from particle data group.
But there are probably some resonances which with unknown.
Yeah, but there are rules for this from SU3 or SU6 symmetries, which can tell you what are the decays. And in fact, these very heavy resonances, which have poor status as particles, they contribute just a bit. So if you take mass spectrum up to 2.6 GeV, so and then increase it up to 3 or more, so nothing changes. In fact, so it's sufficient to truncate at about 2.6 GeV. Okay. Yeah, mass.
Yes, please.
I have a couple of related questions. First is, as far as I understood, you now said that we have separated the confinement transition and chiral symmetry restoration.
Yes.
Is it possible to assume that first is, for example, the confinement and next will be chiral symmetry? Or it's impossible? This is excluded or not?
This is impossible because then we will have to explain the huge number of degrees of freedom. Suppose the first this equation of state corresponds to quark-gluon plasma, but then the number of degrees of freedom is huge. In QCD, we do not see so many elementary massless particles. So then it's impossible. 3 years ago, we still believed that this is the confinement. And only last year, we realized that this is not true. So it is vice versa.
So, but you have a very much
number
of massless particles.
Yeah.
And other related questions is, could you assume other interpretation for this phenomenon, for this phase transition? Or this is unique interpretation, or maybe others?
Yes, we tried, and this is already a result of, I mean, we had other things in mind. For example, that the initial state crosses the phase boundary when energy increases, goes to the quark-gluon plasma phase, and then it goes back again to hadronic phase. But then we ruled out this possibility, and this is what is consistent with everything. Okay?
And the densities which you assume are comparable with the densities which was discussed already from experimental.
Yes.
Okay. Thank you.
Thank you. More questions? Let's thank the speaker again.
Thank you.
The next speaker, Anton Alkin, checked particle multiplicity with Alice at LHC.
Hello, my name is Anton. I'm employee of Bogolubov Institute for Theoretical Physics in Kiev, and through it, I'm also a member of Alice collaboration at CERN, where I'm one of the coordinators of the so-called physics analysis group that deals with all things multiplicity. As was already mentioned by Paul, multiplicity is a very important quantity. Basically, it's a number of particles that were produced in a certain inelastic collision. And it is very important to distinguish between events with a different centrality, basically with a different amount of energy that was spent on producing new particles. So my talk consists of three basically sections. First, I will explain what is multiplicity and how do we measure it in Alice. Then the second section will be about what physics are we looking at with these measurements. And finally, I will show you some fresh results that were already reported at the currently ongoing conference Quark Matter that is very important specifically for our experiment. And these results were obtained within our analysis group. So first of all, the Alice detector looks like this. We have a lot of different components that are described here. We will be concentrating on a few of them. To count the multiplicity, to count the particles, we need detectors that are able to, count. So there are two types of detectors that can do that. First of all, this is, of course, the tracking detectors that basically track individual particles that we can sum up. And there are some detectors that could just produce some kind of amplitude that can be related to the number of particles that were crossing this detector. So, of course, this is the ITS that was already mentioned. Then we have FMD detector, forward multiplicity detector, that is on the sides of it. Of course, the time projection chamber is also relevant. Finally, the ITS itself consists of a few layers that are important, that can be used as separate detectors, in fact. And we have honorable mentions. The AD detector is a new thing that was placed very far at the beamline, so it allows us to extend our pseudorapidity coverage. This is mostly used as a trigger, however. And of course, we have a so-called 0-degree colorimeter that is used to measure neutral particles. And this is very important because it provides the way to estimate centrality for the nuclear collisions. Now, mostly, of course, we are talking about charged particle multiplicity because the detectors are designed to track charged particles because those are easier to track. There are two main quantities that are measured in our group. So first of all, it's multiplicity distribution. Multiplicity distribution is a probability distribution. So we just measure the probability of event producing a certain number of particles within a certain region of the phase space. And there is a pseudorapidity density, which is basically a number of particles per unit pseudorapidity per collision. And finally, we want to measure some other observables as a function of multiplicity, which is very important for physics, which was already mentioned by Paul, because you saw that many plots have multiplicity as in a horizontal axis. So what do we do in nucleons, number of collisions between them, and even the impact parameter, which is very useful, of course, for this measurement. However, for proton-proton, we cannot do that. We don't have any model that can do to the multiplicity. In fact, there are indications that this dependence may be highly non-trivial, and we also have some evidence of the collective behavior in this small system, which is also very intriguing and very challenging. So what do we do here? We want to understand this dependence. And since this is the data analysis basically is the merger between the theory and experiment, so we need to know what happens in the measuring apparatus. We need to know what models can describe that. And here we want to understand this dependence between the multiplicity and the characteristics of this proton-proton collision. And for that, well, we need to start somewhere. We start from two sides. We start with models, and we start with, well, defining some observables that we can measure and see if they can fit into models. How models describe the proton-proton collision? The main approach now is that we use so-called multiple proton interaction. So, of course, the proton in this energy range is not just this elementary particle. This is the thing that consists of quarks and gluons, and well, that's why the typical constituent is called the part of the proton. And the current models employ this multiple proton interaction to produce more particles in the collision, because one thing that we have learned with Alice by measuring these multiplicity distributions, that most of the models before they were tuned to LHC data were severely underestimating the multiplicity that can be produced in the proton-proton collision. It was orders of magnitude. Basically, we see quite a lot of events with a lot of particles produced in proton-proton collisions, and the models were just unable to make them, which was surprising. What next? What processes are we looking here? There is a usual distinction between so-called soft and hard processes. The soft are characterized by particles that have low transverse momenta and mostly by non-perturbative physics. So mostly phenomenology and modeling should be used here. Of course, there is also a contribution from diffractive processes, which is especially important for proton-proton, but this is the matter for other talks. And the situation is better for hard processes, because there we can use perturbative QCD and lattice calculations and this MPI approach. And finally, there is a middle ground, an overlap between the two, which is not yet perturbative, but is also not very soft. Basically, it's not described by either. So this is a quite interesting middle ground that also is studied elsewhere. So what do we have in terms of counting particles? This is the overall rapidity coverage of our detector. So we have the inner tracking system, which SPD, a silicon pixel detector, is a part of. Basically, the innermost part of it. So that's why its rapidity coverage is slightly bigger than the overall thing. And of course, we have TPC, that is, because it's situated farther from the beamline, its rapidity coverage is a bit less. Then we have this forward multiplicity detector on both sides, the V0 detector and AD detector. Now, the colors correspond to different types. So these are the tracking. This is the tracking thing. This allows us to track individual particles. These allow us to count number of particles and do that in the small units of rapidity, while these detectors only just count all the particles in the certain range. So, of course, what do we want to do? We want to know the actual thing, what happens in the collision. However, detector has limitations. So a short remark on what is done to obtain the actual measurement. Of course, there is acceptance. Basically, the geometrical size of the detector limits how much particles it can track. There is an efficiency problem because some particles can be missed for some reason because they have low momentum, for example. Then particles can have very low transverse momentum, and they can be captured by the material of the detector, which also is a problem. And finally, there are secondary particles because material interacts with the particles produced in the collision, and we see secondary particles, and they can be counted as well, which we want to avoid. So what do we do for that? We do the full simulation of our detector. We use so-called event generators that produce simulated collision of the protons or other systems. And then we use that simulated collision, the particles produced in it, we transport them through a model of the detector, and then we use the final thing as an input for the reconstruction, the same as the used for reconstruction of real data. And the result can be then directly compared to the data, and because we know each step, we can trace things from the model that is used in the event generator up to the effects on actual observables, which is very useful for understanding how it all works. And here is an example. For these plots show the correlation between the multiplicity that is generated by a certain event generator and the one that is measured by the detector. You see, first of all, it is non-diagonal, meaning that we lose a lot of particles, especially if we go to the larger rapidity intervals. And there is this random spread that is connected to many factors that I will not describe here, but this constitutes a problem. Basically, if we just count the particles that were produced, this is not the same as the actual number of produced particles in the collision, meaning that we need to relate them to actual thing to be useful for comparison with theory. And it is an involved process, and it introduces the so-called model bias, because to produce this, we use models. We use models embedded in the event generators. And those models can be, well, rather far from data. And if the effect, our observable is sensitive for that particular problem, that means our final result has a model bias, which, of course, makes a very bad physics, because then we produce new models and we compare them to basically bias of the old models, which is not a good thing. So this is something that we try to avoid, and there are a lot of techniques employed to do that. Now, event generators. So these are programs that simulate the collisions. There are many of them, a few examples. And what we have here is an iterative process. So we have a model, we make measurements that are based on that model because we need the simulation. And then these measurements are used to refine the models and introduce new ones. This is something that constantly happens, and our group, our analysis group, is basically responsible for providing the best available measurements of multiplicity that can be used throughout the whole collaboration, and, well, to understand the biases involved and other things. So what can we do about the proton-proton collisions and the centrality? Well, nothing special, but we can start from doing something very similar to what is done for the ion-ion and proton-ion. We take the multiplicity, the measured multiplicity, so not corrected, and we subdivide it into certain regions, basically the percentiles of the total cross-section, not total, inelastic cross-section, I'm sorry. And looking at that, we can try and make measurements in these certain percentiles. So we collect events with a certain range of multiplicities, and we measure something in it, and then we make a function. There is a publication that is being prepared here that will, well, serve as a bridge between what we measure and the theory, so we can use these new measurements to compare the models, because right now it's a bit more complicated. It is actually quite unprecedented thing, because usually the results that are produced are fully corrected. So you can just take those and compare to model. In fact, here we cannot do that because we have something that includes information on how the detector operates, basically what angles does it cover and all the things, and that we have to account for. So this will be something that have to be also accounted by theory to be able to compare to these results, which is quite unprecedented now. Now I will skip this because we have time constraints, but this is basically the reiteration of the fact that we have model biases. We want and we need to avoid them, and there are a lot of things that can be done here on top of what we have already done. And now I will go to the results, which is something that is most interesting here. So first of all, a summary table of what we have already published within our analysis group, quite a lot for all the systems. I will specifically mention that we don't publish multiplicity distributions for ion-ion because, well, main problem in the correcting the data on multiplicity distributions is that we need to do so-called unfolding, no, deconvolution. If you remember that plot with the correlation, that called a response matrix. And using that response matrix, we can employ statistical methods to get from the measured distribution to some kind of estimate of the true distribution. However, to produce such a response matrix, we need to produce a lot of simulated collisions with high multiplicity. And that is very time-consuming because we need not only to produce them, we need to pass them through the detector simulation as well, and this requires an enormous amount of computing resources. This is not something that can be done in a realistic way. That's why this is usually excluded. However, we have plans for that, because that can be done. We have a lot of resources, we can use them. And of course, pseudo-rapidity density is a more simple quantity. It can be done for all systems, and it is very important for them. Now, first of all, the multiplicity distributions for proton-proton collisions. Now, this is at 7 TeV, the best we have available now. The result for 13 TeV, the latest LHC energy, is being prepared. This is in different pseudo-rapidity intervals, from the most central to the widest that we can use in our detector with the FMD counting. Now, this is the result for pseudo-rapidity density in PP compared with the models, the contemporary models at the time of the publication. Now, they may perform better, but then they were quite far from the actual thing. This is very interesting plot. This is the preliminary result for proton-ion collision, and this is the pseudo-rapidity density. Of course, this is a ion region, ion fragmentation region. You see that models actually do pretty well at the ion side, but very wildly at the proton side, which is a big problem. I mean, we have a good hydrodynamic simulation for the large system, but we have still problems with the small one. Now, pseudo-rapidity density binned in centrality, so going from most peripheral to most central collisions up here, and this is for two energies, 2.76 and 5 TeV. And this is for ion-ion, of course. This is also ion-ion, but the smaller ions, xenon ions, a very recent result, very similar to what we had in lead-lead, and also a comparison with models that also seem to not perform very well. There are some doubts at this region. You see, even the shapes are different, so we have still some things to do. And this is the cherry on top. This is the proton-proton collisions subdivided into multiplicity percentiles. This is the very fresh results, and it had a lot. We put a lot of effort into obtaining it because we had to account for a lot of uncertainties and biases. And unlike the iron-iron, this has less statistics to work with. However, you see there are some results. And to showcase what is happening, so this is the same results but integrated. And as we go to the most multiple collisions, the multiplicity of those grows with energy faster than those of the less multiple collisions, which is something that we have seen for centrality in larger systems, but not something we expected this for protons, but we still have no proper explanation for this. And this leads me to conclusion. What we have is a very comprehensive set of multiplicity and related measurements that we have produced within our group, and we have provided a framework for people within the collaboration to, do their own multiplicity-dependent measurements without bothering too much about biases, because we worked hard to remove those biases from the framework. And since we have a lot of data now on all the colliding systems, we can start, because we now have also for PP some kind of centrality-like measurement, we can start with comparing colliding systems with similar energy densities, but very different volumes, extremely different volumes. In fact, the most peripheral iron-iron collisions are still much significantly larger than those the proton-proton. And despite the multiplicity being very simple, observable in just number of particles, there are a lot of effort involved to get the physics results from it. And this works as the bridge between theory and experiment, because you need to understand both to go from the measurement to the result and from the result to theory. And still, we have a lot of models, but for proton-proton, they're still struggling to explain what we see in the reality. Thank you very much.
Does somebody like to put questions, comments? Please.
Do we have a special, pay special attention for PP events with very extremely high, very multiplicity?
Well, we did.
Small physics, small system physics. So,
yes, we did. However, there are purely experimental limitations. First of all, these events are still rare, despite the fact that the models underestimate their probability. Their probabilities are still small. And we need to do something with backgrounds, and we have a trigger that has a limited rate, so there is a problem in collecting enough of those events to do some analysis on them. But this is an ongoing effort, of course. There were a lot of work involved by some dedicated task forces that were specifically using that, and we are still trying to, there was an idea to make this special high multiplicity trigger that would select effectively the events with high multiplicity in proton-proton. These efforts are still struggling to produce a result that can be used for physics, because a lot of background is involved, a lot of.
Okay.
This modification of the detector will be playing for this upgrade next year.
Oh yeah, no, the upgrade will help a lot with this. Yes.
Yes, please. Yeah, your question.
Could you obtain multiplicity as a function of transverse momentum?
Of what momentum?
Multiplicity as a function of transverse momentum. Could you obtain?
The transverse momentum is something that characterizes the particle, while the multiplicity is something that characterizes the event. We can do vice versa. We can look at the multiplicity dependence of average transverse momentum. And actually, there is a publication in Alice that shows exactly that. And we see some function that seem basically the transverse momentum, the average transverse momentum of an event grows with multiplicity, but the growth becomes smaller. It may be going even into saturation, but we are not there yet. It's too far we cannot measure that far yet.
Okay, let's the speaker again. And I'd like to give the floor to Yuri Sinyukov. It's development of the space-time picture of nuclear collisions. 20 minutes.
Thank you. First, thanks to organizers for opportunity for me to present our results, old and but principal and very fresh one here. And I'm talking on behalf of the group of the researchers. And many of our results were obtained in close cooperation with Alice collaboration, especially market. In heavy ion collisions, the initial huge kinetic energy of collided nuclei converts into masses of the final observed particles. We have several tens of thousands such secondary particles, and plus this energy converted into energy of collective flow, not only initially longitudinal, but very serious and very strong transversal flow. It's up to velocity of light, in fact, 0.7. So in this case, it's not very non-static system, and the results which obtained for static systems should be applied with big caution for this system. Here is cartoon of such kind of collisions. We have some time scale. This time scale to establish it also was use our formulas. And we have colliding nuclear. After that, for LHC energy and for Rick energy, we expect Vogel plasma. And this is pre-thermal dynamics, which very complicated one. And finally, we have free streaming and this. This cartoon, we realized during a few years in so-called integrated hydrokinetic model. The complete algorithm incorporates the following stage. First, we create the very dense system at 0.1 Fermi. This is initial state. You use Monte Carlo Sitenka-Glauber approach. And the second, it's only our model among others in the world uses thermalization of initial non-thermal matter. It's this stage from 0.5 Fermi to 1 Fermi over here. After that, viscous relativistic hydrodynamics in Israel's pure form applied. And of course, we cannot apply approximation of the continuous medium up to the end. It decays into separate hadrons in hadrons, and this it's a stage of decoupling, it's particularization stage, and after that it's very interesting stage, by the way, and which modify many results which one can ignore if you so-called freeze-out conception. It's evolution with an interacting hadron gas, and after that it reached to apparat. And so, because we consider basic standard model for this process is hydrodynamic-based model. We use hydrokinetic. It means that we pretend to describe soft physics measurement, not all measurement, but only soft physics. Soft physics include what Arkin-Dog, this particular number for different particular species. It includes spectra, and it includes correlation function of different time, two and many particles correlation function. And here it's hidden the information in the slope of the spectra, hidden information about collective flow, because effective inverse slope, it contains this factor transverse flow and also without temperature. Also, of course, this particular number ratio contains information about chemical potential and temperature near hadronization. And but because my talk devoted to space-time picture of this collision, we concentrate mostly on the correlation function of identical particles. If we consider two identical particles which emitted from Xa and Xb and build them in momentum representation as a wave function, in this case, after we ask about probability to find two particles momentum P1 and P2 that emit from X1, Xb, we obtain this specific term which contains a distance between point Xi and V, and if it is region and these points distributed according to Gaussian, finally we obtain correlation function or probability which Fourier image of this R. So the width of the correlation function in difference of momenta give us inverse size of the source. This initially resulted in invention of Kopolov-Podgoretsky. We, during few years, transform from some tool which allow to measure, interpret, and use for heavy ion collision. In fact, we propose 3 results which are basic for all group which do with interferometry. First of all, it's a so-called one of the femtoscopic scales, the interferometer radius, which are directly connected with lifetime of the fireball, which creating heavy ion collision. And this is method which used for 40 years to measure this time of existence. Another general interpretation was done. We measure not sizes of the system, but homogeneity lengths. And next was basic results, which called Bowler-Sinyukov treatment. The method that was developed that allowed to separate the quantum statistical correlation because identicality of the particles from Coulomb and from London resonances. And in fact, what we measure not total size of the source as Kopolov-Podgoretsky thought, but we measure only part of the system which create homogeneity lengths for particles which have momenta P in the distribution function. So there are a few directions, and a few directions along beam axis, along some of the moment of the particle perpendicular to this one. All this homogeneity lengths, just our radius, but so this is one so-called out radius, contain 2 terms, which it's the duration of radiation from the surface of fireball and correlation between time and the transverse radio transversal direction of the emission. And quark-gluon plasma was associated from very beginning at this time because conversion of plasma into hadrons, it's large enough, and this radius gives us. And the experiment brings the so-called RIC HPD path. It is unity. And we really found that at our first calculation that here is quark-gluon plasma, nothing emit here. Here is time. Here is transverse radius, and we see here is maximal of emission. But we see that for SPS energy, RIC energy, larger, and maximal at RIC energy, it's emission, total emission. But the slope becomes more and more, and because this correlation eats this correlation, and finally we predict that it will be near unity for LHC energies. This prediction was a few years ago because experiment was done. This is a quotation from a very first paper of LHC devoted to femtoscopy analysis. And they wrote here is this famous around to Earth side ratio, and they found that only 2 models are able to describe the experimental out-to-side ratio. In fact, only our model, because second model is this line. I don't see that it's good. Our really describe it. We consider also analysis of interferometry volume. So it's volume of region of homogeneity at different transversal momenta, but it exists at the product of all sizes and all direction related to this homogeneity. And we found that without post-hadronic, without so-called afterburner stage, it's after hadronization. Without active, we cannot describe this radius. And if we include the interaction after chemical freeze-out, so-called chemical, we obtain good description for different energies, AGS, SPS, low SPS, high, RIC, and LHC. And it's very interesting that we try to describe with the hydrodynamics the proton-proton. Here's proton-proton. Here is lead-lead and gold-gold central collision. Here is proton-proton. And it was not possible, as we see. But when we take into account the uncertainty principle, small system which creating proton-proton, after that we get very good description. And we see that very interesting results. That the interferometry volume, what's this volume, depends not only on multiplicity, you see more particles, more larger volume, yes, but also depends on the initial size of the system. It's A, okay, but it's initial size of the system. And we have very good description for LHC. It's not fitted. It's fitted by multiplicity. We fit few parameters in our model. From multiplicity depends on centrality. It's just prediction. So this is good description of all radius. Also, for RIC we calculated, it is written that the results are in favor of the hydrokinetic prediction. 23, it's our paper over pure hydrodynamic model calculation. So after hydro stage, it's very important, very fresh results. This, which it was end of the 2017, it's a this collaboration. It is transparency, not mine. It's transparency from work-matter report of this collaboration. And you see so-called averaged interferometry radius, and it is radio for kinds show good agreement with HKM prediction. It's our paper for K+. Also, three-dimensional radii, also very good described. And what is very important, it will be not good described if we have no rescattering after hadronization happens. In this case, HKM model without rescattering demonstrate approximate MT scaling. MT it's a mass square and plus momentum square root. So everybody expects that MT scaling, but we have not MT scaling, but we predict KT scaling. So, but not MT. And radius scale better with KT than MT according to our model. It's also from transparency of Harris collaboration. And very, very new results is concerned that that we see the scaling will be also for 5.02 TV. Okay, thank you. And here's a realistic picture of what happens in heavy ion collision. And again, here is time, here is transversal radius, here is nothing emitted from point of view of hadrons not emit here. Here is a maximum emission, and here is also maximum emission. There are second maximum we can see it only numerically for K. And we develop our initial formula, it's my formula, and develop now, I also do it in 15, for formula which take into account very strong collective, transversal collective flow. And this collaboration applied this formula and found that maximum radiation of Cairns happens at 11.70 Fermi-OVC, while for pions, maximum emission at 9.3. It's very interesting result in the sense that necessary to be understood from where this second maximum appears, and for this aim we analyze so-called K-star probe. K-star probe, K-star lifetime is near 4 Fermi-OVC, so it appears at hadronization. After that, live near 4 Fermi. And what we studied, this is without surrounding, without interacting gas. This is with interacting gas, a picture of decay of K-star. We use absolutely like experimentalists, try to see invariant mass of the particles of the product of decay, and also here, but with surrounding and in fact in non-interacting surrounding after hadronization. And we found that only 30% or even less survive for experimentalists, because K plus and pi minus start to interact with surrounding and be lost invariant mass. And finally we get after that that we have only 20, but we have not only 15 Fermi, but all time. It means that at least 50% of K star create in the medium which appears after thermalization. And it's confirmed that we really found this number, okay, because it's beautifully described spectrum of K star according to this. So this, I am finishing, try to finish as soon as possible. You see, here is our calculation for particle number ratio. We also consider in dynamical models, we have no chemical freeze out. And we see, for example, it depends on that we have better description pi plus proton plus pion when we have dynamics after sudden freeze out. So no sudden freeze out there is, and we have something in addition. And I show my final results. It's a conclusion, and there is not only hadron probe, but we consider it's today. This paper was published just today. It was so here's even no number, but now it's published today. And this paper it's about penetrated probe. So we see all dynamics, and we can see using photons not only that happens outside of plasma, but from inside of plasma. It's signal from inside of plasma. It's photons, and we found very interesting results that we more or less describe data. Also, its transversal momenta, its anisotropy transversal momenta expresses in V2 coefficient in Fourier transformation. But what we found that if one supposes that during hadronization, process of hadronization, there is mechanism which, for example, when two quarks which are charged particles form hadron, if this mechanism is accompanied by photon radiation, we have essentially improving the results. Its results become very, very good. And in fact, and because this is maybe paper published, because it's a new mechanism. So what is summary? The theory, method, and interpretation of the correlation femtoscopy that we develop, for such kind of analysis for A plus A, proton-proton collision. and it allows to restore space-time evolution. And the integrated Cern-UA mill was developed that describes the soft physics and ultra-relativistic RIG and LHC accelerator, and gave many important predictions confirmed in experiments. And our prospects, because we describe so many, it's only part I show results. And now we try to go to low energies, which is very complicated stuff, but we will do it. Thank you for your attention.
Thank you very much. Congratulations with the today publication.
What?
Congratulations with the new publication
Yes,
which
yes.
appeared today.
Today is for photons.
Yes. So please, questions, comments. Please.
Yeah, it's interesting, of course, and the results are very nice. But the question is, you see, why we're trying to explain the nuclei, it's very important, because last year Cern-UA and his team claimed that fluctuations of light nuclei really can serve as a signal of critical, or we believe, critical endpoint. So my question is, did you try to describe deuterons, antideutrons, tritons, and helium?
This is
Or
for
not?
was not. It's for LHC energies, and we of course, you see, we should create mechanisms that not only statistical hadronization, yes, which we normally use, but we should use mechanisms that give us light nuclei. This is what we have. No such mechanism that should be introduced here in addition to this one.
Thank you. More questions? No question. Let's thank Yuri again for excellent presentation. And the next speaker, Igor Tymchuk, Lead Technologies of Ukraine for some current status and prospects.
Okay, so I'm a representative of Lead Technology of Ukraine company and a team leading by Professor Borshev, and I'll give you a brief overview about our current activities for CERN and our prospects and future plans. So, in this presentation, I'll give a few words about our activities for physics experiments, but also a few words about our current status, so namely this ALICE ITS upgrade project, and also our future plans as activities for ALICE focal project, what actually preliminary was mentioned by Paul. So our activities of our team for physics experiments are directed on development and creation detector modules and their components, and also manufacturing ultralight interconnection elements based on adhesiveless foil dielectrics. And also we are developing assembling workflows for detector modules as well as their components, because these modules are enough complicated devices. But also we are developing some precise assembly and technological jig, but also some tool for assembling such devices. So then our current status is participating in ALICE ITS upgrade project, and main our partners in this activity are of course CERN, but also some laboratories and institute from the USA, but also from the Europe, like LBNL from the USA, but also INFEN and NICAF from Europe. So that on this slide are given schematical view of upgraded inner tracking system for the for this project, and our part is actually main part of this inner tracking system, so-called stave, and here is given, let's say, part of our responsibility, these micro cables for power supply system for such detector part. And also we are responsible on development and production so-called micro cables like power bus, bias bus, as well as cross cables. Also, I would like to say that within last few years by our team, some R&D on creation of detector modules based on novel maps sensors also have been performed, and prototypes have been successfully tested at Cern. So then more detailed what we are doing for ELISA ITS project. We are developing and now we are producing and we are delivering micro cables for this inner tracking system. And what is other features of such micro cables? First one is that all of them are realized based on materials with aluminum conductive layer, what allows to obtain as lower material budget as possible in fiducial area. Also, then actually it is foreseen that will be delivered three types of micro cables. First one, so-called power bus, actually, which is multi-layered, multi-component cable with a length up to 1.6 meter. And these such cables include up to 80 components per one cable. But also we are producing so-called bias bus, which also multi-layered cables, but up to 6 layers in some parts, and also such cable includes up to 30 components. These two types of cables are enough complicated and multi-component, but their required amount for ELISA ITS project is not so high. And you can see that we need in total power bus about 400, but as well as bias bus. Third type of cables which will be delivered for this project is so-called cross cables, which are foreseen for connecting power bus and bias bus with as a part of stave. So in total, it is foreseen delivery about 16,000 of components, and actually main production is foreseen for this year and few months in next year. So, but for let's say for reaching this contract, which by the way was signed between Cern and our company September last year, a lot of efforts have been applied by our team within last 3 years, and here you can see a brief, let's say, evolution of development of our team for this ELISA ITS project. And actually, first our proposal was given end of year 2014, and after this, approximately once per 6 months, we developed and we produced some prototypes, mock-ups, and so on for final, let's say, signing of the contract September last year. But after signing of this contract, also it's foreseen a few steps which are given on this slide, and actually now first 3 steps are passed by our team, and since March this year, actually we have, let's say, final part, production stage, and it's planned within the contract that till February next year, all mentioned before components will be delivered at Cern for further using for creation of this upgraded inner tracking system. New materials have been developed by our team, and also some technologies for manufacturing components and also as cross cables. Production, and actually now production is ongoing. So, and all of these things actually these novelties as well as know-how were successfully tested on a real prototype, a real functional prototype of stave. And here you can see photo of first functional prototypes, and here are given, let's say, our components. And this was photo was taken at CERN end of last year. So then, as pre-conclusion on this part of my talk, I would say that our team and our company applied a lot of efforts for successful cooperation with CERN within this ITS upgrade project. Also, contract was signed in September last year, and it's foreseen delivery about 16,000 components, and actually about 3,000 of them are delivered already now. So, and now we have stage that we have production stage. So then second part of my talk is Alice Focal project and main our partner here, of course, CERN, as well as NICEF and as the University of Bergen. So then here our part of activity is also more or less similar to previous one, but we are developing with very close cooperation with the NICEF team. We are developing multi-layered flexes as well as also other interconnection elements, but also assembly workflows is developing by our team, and also some jig with NICEF team also is under development now. And but we joined to these activities a bit more than 1 year ago. So our part is, let's say, at this moment is so-called high granularity layer, and which is foreseen to be built based on also this novel MAP sensor. So, and these some features of our approach for this focal project is that our approach allows to guarantee that for assembly of slabs will be used only functional maps and will not use any bad or defected chips. And also one thing that our technologies allowed do not use wires, what allows to increase reliability and also increase, let's say, decrease amount of bonds. So, but as a first step for this focal project, it's foreseen creation so-called M-Tower, this spectrometer which for investigation of these chips and also technology. And also for this part, our part is, let's say, this multi-layered flex, but as well as chip cables and also assembly technology and workflows for such device. So that presently by our team within last year, beginning this year, were performed following activities. So it was were developed approaches for realizations both as slab as well as M-Tower, and also workflows have been developed, and all of them are preliminary verified during creation mockups and as well as prototypes. So then on this slide are given photo of technological mockup which we developed and produced for checking this assembling and some design features. And now beginning this year, a prototype of such detector layer have been developed and provided for NICEF and University Bergen teams for functional testing. Then for slab, we developed and produced some technological mock-up for checking some, let's say, technological and design features. So as a conclusion on this part of our talk, I would demonstrate, let's say, our plan for this year, but of course now this under revision and something will be changed, but at least it's foreseen to produce additional mock-up and prototypes, and also, let's say, before mentioned M-Tower. So, and further steps will be discussed and defined, I think, this year or next year. So then, as a final conclusion of my talk, I would say that our company and our team, let's say, have current status like ALICE ITS upgrade project, and now production is ongoing. And further, our plans, at least this ALICE focal project, and in additional, I would say that our company also participating in some other physics experiments, like the CBM experiment at Darmstadt in Germany, but also we are at R&D stage for experiment Panda, also at GSI and in Germany, as well as MU3 project, which will be carried out at Paul Scherrer Institute in Zurich. So that's it from my side. Thanks a lot for your attention.
Thank you very much. A very impressive talk. Please, questions, comments. Everything is clear.
It's great. Thanks.
No comments. I think that it's very nice that in Ukraine we have now high technological company, and this company contribute to Cern-UA cooperation. Congratulations. Yeah. Thank you very much.
Thank you.
Okay, and now the last speaker, Alexander Demin, Grid Cluster UA ISMA as a constituent of the Tier 2 Center of ALICE experiment.
Dear friends, dear colleagues, my name is Alexander, and my report is devoted to the computational process of ALICE experiment and how our institute took part in this process. So when Large Hadron Collider was projected, the ordinary way to process data from experiment was to set up a standalone supercomputer. But at this time, there was understanding that standalone computers have a threshold in its power, and this threshold is very near. To choose was not a supercomputer, but a distributed system grid. What is a grid concept, and what means this word? Usually, most of people concern this word with network and imagine that this means computers inside of any grid. No, this word comes to phrase power grid. And concept it like power grid concepts. When user turn on power, he don't need to know when and where this power was produced and how it was transferred to user. So concept of grid is when user need some calculations, he connect to grid system and gives us calculations and he don't know when and where this calculation was proceeded. Grid is consists of computational clusters which is connected through internet, and each cluster consists from computers which is connected through local network. Usually it is a dedicated, very powerful network. In our institute, we begin to construct such cluster nearly 20 years ago, and this is how it looked like in the beginning of our age, and this is how it looked like yesterday. Volume is less, but number of processors is more, and power and calculation facilities is much more. But this facilities is miserable comparing with Cern clusters. And this is only one of Cern clusters. In each Cern collaboration, clusters of members of collaborations are structured in a few levels. Tier 1 is placed in Cern, and its purpose is to receive data from detectors and to transfer it to Tier 1. Tier 0 is connected. Tier 1 receive the data, save it to storages and proceed data. Proceeding is paralleling and distributing process, and it's distributed between Tier 2 sites. So the purpose of Tier 2 site is to receive job from Tier 1, to complete it, and to get back result. The cluster of our institute is the Tier 2 site of ELIS experiment. We take part in the calculation by ELIS since 2009. In this year, we install all the necessary software, install middleware Light. Middleware, it's something like operating system, but not for computer and for all cluster. And begin to calculate with ELIS data. This is a chart for all time from beginning to our day, how much jobs we calculated. There was peaks and bottoms. There was a period of stop our collaboration, but in all, we take part in this. The most fruitful was 2014 year. In this year, we produce half of all Ukrainian calculations in field of high energy physics. And as for ELIS, our calculation was a lion part of Ukrainian income. But this lion part was very, very small comparing with all contributors. So our main achievement was that we don't merge with the horizontal axis. This is our ELIS collaboration have profit from our institute not only from calculation. We always use the latest version of software. We are in the avant-garde of upgrading, and that's why Nolens Volens, we are beta testers of this software. And several times we found it backs and reported back to developers, and one time the solution of this bug leads to changes not only in ELIS software but in libraries of Linux itself. A few words about structure of managing of our cluster. We strongly follow the principle one service, one computer. it makes minimum fault of all system. But if we use hardware computer, this is very efficiency is very low, because usually service use very low part of resource of computer. So we in our cluster we use virtual computers. We have pool of nodes. This is real hardware computers, and we have a pool of services of virtual computers. And we put virtual computers to nodes, and that's why we can balance run of each node, and you can see that percent is quite big. And you can see that uptime of this physical computers is more than 1 year. So we can restart any virtual server and not restart a physical computer. And this system allows us to change software, to make upgrading very easy and fast, because we organize new virtual computing, install all software to it, and then change it with old virtual computing. So it is not produce reloading of all system, and it is invisible for our users. So I told about pool of services, and our main problem is in this calculation is not a technical problem, but organizing problem. You may see gaps on our charts in the time. This gaps problem is that we have slightly an understanding part in collaboration, because no one of our programmers don't have a certificate to change or even to run Alice software on our cluster. So while we have excellent availability of our resources to Alice computing, when we have any problem, hanging of software or something like this, we need to solve this problem, but by very complicated way. And if a problem can be solved in minutes, it's solved in hours. Instead of hours, we have days. So our efficiency is lower than it can be. Nevertheless, last year we have 17% of all Ukraine calculating in high energy physics calculations. Our future plans is to continue cooperation, to implementation new technologies and services such as cloud service, new network file system, and the testing of new versions of middleware software for HPC and high energy physics. Thank you for your attention.
Please, questions, comments? Yes, please.
You said that the efficiency is lower than it could be,
Yes.
partly because of bugs that are not solved quickly. But earlier in the talk, you said that you use virtual machines and that you test new versions on a single virtual machines first. So I don't understand the relation.
Yes, but we don't have appropriate certificate to run Alice software. So when we need to rerun it, it runs from certificate of another people. Usually it was Oksana Shadura from Theoretical Physics Institute. And when she is busy, problem is not solving. We know how to solve, but we don't have rights to do it. We need to use rights of Oksana. We call she and ask her to do something, and only after she do this, problem solved.
Yeah. Did you discuss
this
that?
only organizational problem?
Did you discuss that?
It was a problem which started to be solved, but they was interrupted because of illness of Gennady Mikhailovich. He is the leader team. I think that during quite short time it would be solved.
Yes, I think that's not crucial problem. It
Yeah,
could be
not
solved.
crucial, not crucial.
It just takes a little bit time.
But very long problem.
More questions? No questions. Let's Alexandra thank again. Dear colleagues, program of the session and as well as the program as the whole conference is complete, and we can start the closing ceremony. So, dear colleagues, a couple of thoughts. First of all, I think that the conference is a success. We had the possibility to hear about the recent developments in Cern, and we had a lot of presentations from the Ukrainian side. So, first of all, I'd like to thank all the participants for their participation in the conference. Of course, I'd like to express our appreciation to the Cern delegation who presented nice talks about the recent developments in various collaborations, the ALICE collaboration, LHCb collaboration, CMS, CLIC, and so on. And I think that it was very, very useful for us, at least for the Ukrainian part, Ukrainian participants. Of course, I think that we can express our gratitude to the organizers for their warm hospitality and for nice organization of the conference. And here you see the draft of resolution of our conference. Our conference collected about 70 participants. About 10 institutes and universities of Ukraine, representatives of about 10 universities and institutes been present here, and of course, it is very, very useful for us. I can I'd like to show you the draft of resolution. There is some general part describing what is our conference, what was our conference, how it was organized. We also express our gratitude to the organizers and to the CERN delegates, and I'd like to draw your attention to this part of the resolution. First of all, we would like to point out that fundamental science has a very important role today, and taking into account importance and fundamental character of the research work at CERN, the international cooperation with CERN should be one of the first priorities for Ukrainian high energy community. The conference has demonstrated rather high level of research carried out by the Ukrainian high energy physics community, despite some current difficulties with funding. The existing staff potential and is still high research level in selected branches of this field ensures the possibilities that Ukraine CERN cooperation can be of mutual benefit. The next point is concerns the education and the importance of collaboration with CERN concerning the involvement of our students, PhD students, to the school, to the program, CERN program, educational program, and it would be very important for us. We also would like to point out that the available financial support of the research in high energy physics in Ukraine is obviously insufficient. We shall prepare a request to the Ministry of Education and Science, to the government, to find the possibility to increase our budget. Of course, there is no doubt that the cooperation with CERN should be further enhanced. And finally, it was there were some proposals that this conference is rather interesting for the Ukrainian participants, so we can also propose to organize such conferences on the regular basis, at least once or 2 or 3 years. So this is, of course, this draft should be edited a little bit, but now if somebody like to propose something else, you are very welcome. So this draft of resolution is open for discussion. Please, if somebody like, you can add something. It will be possible also to do a little bit later. This draft of resolution will be distributed among the participants, and we can formulate that. We can prepare the final version in a couple of days. No proposals. Sorry?
It's necessary to recap.
Okay, I repeat that this draft will be distributed between the participants, and we shall take into account all reasonable proposals. Yes, please.
This is 30 million for support. Now we have something.
It is our dream. You know that now the budget for high energy physics research in Ukraine is rather modest. We have a TAGIS program in the Academy of Sciences, and the budget of this program is about 2.5 million of Ukrainian hryvnia, so it's very small. And we shall also ask to allocate some budget in the national research fund, which should be established in the nearest future. Deputy Minister Striha told about this 2 days ago in his presentation. So we expect that this National Research Fund will allocate some special budget for high energy physics research. But in any case, we have to knock the door and try to get positive response. Any comments? Approve in general, and then we can introduce corrections based on the participants' proposals. Okay, thank you very much. So I have to thank everybody once more for their participation. I'd like to wish you new successes in high energy physics. I wish our guests to have a bon voyage to their home, and all the best. And let me announce that the conference is closed. Thank you.
Dear colleagues, on behalf of organizing committee, we also want to say thank you, all of you, and we prepare small video. And also, I want to invite all our speakers today also to the lunch here in second floor.
Okay.